Hi, I'm Norman Wallberger. We're returning to universal hyperbolic geometry, our study of a new way of thinking about hyperbolic geometry purely algebraically, without any transcendental functions or infinite processes, a much cleaner, more beautiful, more logical subject. And in the last few videos in this series, we've been actually looking at the sister geometry called elliptic geometry, which is pretty well the same as spherical geometry from practical point of view, although there are important theoretical differences. So we can visualize things by thinking about a sphere in three-dimensional Euclidean space. And we have 3 points on that sphere, giving us a triangle called a spherical triangle. Actually, the really mathematically important objects are the lines that those 3 points determine with the origin or the center of the sphere. So if we have a sphere and we have this origin, we have a line through the origin. It's really that line which is the projective point that we're interested in. And we have maybe 2 lines, and then if we have a third line, then that's really an elliptic triangle. That's really the main object of study here. And we visualize that by drawing a sphere centered at the common origin and giving the points where these lines meet the sphere, or at least approximately meet the sphere. Because not all lines through the origin necessarily exactly meet the sphere. Okay, so we have one of these elliptic triangles, say A1, A2, A3. There's our notation for it. And associated to this triangle are 6 numerical values, the 3 quadrances and the 3 spreads. These are the basic ingredients for the elliptic or spherical trigonometry. So what are these quadrances, Q1, Q2, Q3, which are shown here? There's Q1, Q2, Q3. That's our notation for these projective quadrances. Now these are projective quadrances, so they're really quantities associated to a pair of lines. We have a pair of lines like this in three-dimensional space, the space that we're living in, and we want to associate a number to this pair of lines. Okay, it's a fundamental basic measurement. Okay, the number that we want to associate is not an angle. Crucially, it's not an angle. Because if it was an angle, we would have to fuss around whether we're talking about this angle or maybe this angle. We would actually have to fuss around what the definition of an angle is, involving calculus notions and infinite processes. All right, so the definition of the spread between these 2 lines, or for us the projective quadrants between the corresponding projective points, is much simpler. We take a vector, say v, v1, another vector v2, in these 2 directions. It doesn't really matter how big those vectors are. And we look at 1 minus v1.v2 squared over v1.v1 times v2.v2. It's a basic formula for the projective quadrants between these 2 lines. It doesn't matter where those vectors are, you always get the same number. It's a number that's 0 when the 2 lines are parallel like this. It's a number that increases up to a maximum of 1 and then decreases down to 0 again. Okay, very nice, clean, elegant measurement. A fundamental basis for rational trigonometry. Okay, so those are the quadrances, and what are the spreads? Well, the spreads are very much the same kinds of things. The 3 points that we have, are these 3 lines of the origin, determine 3 planes. And those 3 planes have normal vectors, or normal lines. And so the spread here is just the same kind of projective quadrants between the normal to this plane and to this plane. So it's really the same kind of formula as defines a projective quadrants, defines a projective spread. And since everything we're doing here is in this elliptic context, I'm not including the adjectives projective everywhere. Okay, and so let me remind you of the fundamental formulas relating these 6 numbers. The spread law asserts that S1 over Q1 equals S2 over Q2 equals S3 over Q3. The cross law is, well, there's actually three such laws, one for each of the spreads. So this is the formula that tells us how to calculate capital S1 if we know the three quadrants Q1, Q2, Q3. S1, Q2, Q3 minus Q1 minus Q2 minus Q3 plus 2 all squared equals 4, 1 minus Q1, 1 minus Q2, 1 minus Q3. That is the cross law in this projective setting. And if we wanted to know something about S2, we would replace this first term here with S2 times Q1 times Q3. The rest of it would be identical. If we wanted to know about S3, we would replace it with S3 times Q1 times Q2. So there's really three symmetrical cross laws. And then beautifully, there's a dual cross law obtained just by replacing the quadrants with the spreads exactly, verbatim. So it allows us to calculate a quadrant, say Q1, if we know the three spreads. It's the dual cross law. So really, there are fundamentally two crucial laws in this subject. And this is quite a serious law here. It takes some getting used to. You may think it's unnatural, but it's a very, very beautiful formula with a lot of interesting consequences. And for those of you who have studied the Universal Hyperbolic Geometry series up till now, which I hope is most of you, you will be familiar with these laws. They are already the same laws that appear in Universal Hyperbolic Geometry. So what we're seeing here is a unification between hyperbolic geometry and elliptic geometry. They're driven by the same metrical formulas, namely these two formulas right here, ultimately. There are now a few important special cases. One of them is when our 3 points are all in a plane. So the 3 lines to the origin that we're considering are all in a single plane. Geometrically, the points on the sphere that we're looking at are then all on this great circle. So we have then the quadrants Q1, Q2, and Q3 satisfying this triple quad formula. This is what you get when you take the cross law and you set that spread, say S1 equal to 0, then the rest of it becomes this law here. Q1 plus Q2 plus Q3 squared equals 2 Q1 squared plus Q2 squared plus Q3 squared plus 4 Q1, Q2, Q3. So this is the projective triple quad formula. And in ordinary planar Euclidean geometry, this same formula is called the triple spread formula. So it plays sort of different roles. Absolutely key formula in mathematics. Another special situation is when we have a right triangle, like this one here, where we have this great circle and this great circle perpendicular. Or in terms of geometry of the projective plane, if you have one plane through the origin and another plane through the origin which are perpendicular, like this, and then there's a right triangle there, or a spread of 1 there. So if S1 is 1, then there's a few special relations that happen. In particular, there's this Thales theorem, which is basically just an immediate consequence of the spread law, which says that S3 equals Q3 over Q1 and S2 equals Q2 over Q1. So for example, S2, this spread here, can be calculated as the ratio between this quadrant's Q2 and this quadrant's Q1. So opposite over hypotenuse. And that's a very nice sort of aspect of similar triangles, connecting with sort of familiar planar trigonometry. If you move this line so that it's cutting this base line still perpendicularly, then this ratio of this quadrant to this quadrant will always be the same, will always give you that spread there. And another important relation is that in such a right triangle, the hypotenuse quadrants is this quadrant's Q2 plus this quadrant's Q3 minus the product of these two. This is a variant of the planar Pythagoras' theorem, in which there's no quadratic term and just Q1 equals Q2 plus Q3, our basic planar quadrants formula for Pythagoras. Okay, there's also sort of dual formulas where we have right triangles where not just one spread is equal to 1, but rather one quadrant is equal to 1. Since the quadrants and spreads are completely symmetrical, whenever we have a formula we can replace it with the sort of inverted formula with the quadrances and spreads interchanged. So in mathematical theories where we have complicated formulas, it's really important to solidify our understanding by working through examples, preferably starting with simple examples and then working your way through more complicated ones. So let's do that. Let's start by thinking about how does this all work in a specific concrete example where we can work things out and check that our formulas are true. So let's choose a particular example, and I'm going to choose relatively simple vectors. The vector 1, 0, 0, we'll call that v1, so there's the vector v1 in the usual x, y, z representation of three-dimensional space. v2 is 0, 1, 0, unit vector in that direction, and v3 will be 1, 0, 2. So the vector 1 in this direction, 0 in the y direction, and 2 in the z direction. There it is right there, v3. So this v3 is in the plane spanned by the x and z axes. It's no longer a unit vector. So the corresponding lines through the origin determined by these vectors are written like this. We have our sort of homogeneous convention. We're using a proportion there, the colons representing proportions, telling us that we can scale this object by multiplying all three entries by a factor, and we agree that nothing changes. So A1, A2, A3. Okay, so let's calculate a few quadrances. What would be the quadrants Q1? The quadrants between the V2 and the V3 direction. So here's the formula. It's 1 minus V2 dot V3 squared over Q of V2, Q of V3, where Q of V2 just means V2 dot V2. And we're talking about the usual familiar Euclidean dot product here. So V2 dot V3. Here is V2, here is V3. If we take the dot product, it's this 0 times 1 plus this 1 times 0 plus this 0 times 2. That's the dot product. All those terms are 0, so we get 0. 0 squared is 0, and we get just 1 for the quadrants, telling us that these two vectors are perpendicular, as is sort of obvious geometrically. How about Q2, the quadrants between V1 and V3? These are no longer going to be perpendicular. So the V1 dot V3, here we are up here, so the dot product is 1 times 1 plus 0 plus 2. It's a total of 1 up there, and so 1 squared is 1. The quadrants of V1 is 1 squared plus 0 squared plus 0 squared, that's 1. The quadrants of V3 will be 1 squared plus 0 squared plus 2 squared for a total of 5. So 1 minus 1/5 is 4/5. That is the quadrants between these two vectors, the projective quadrants. And Q3, the quadrants between A1 and A2, is pretty obviously 1 because they're perpendicular. Okay, how do we find the spreads formed by these three lines to the origin? So in other words, there's three planes involved. There's the XY plane, there's the XZ plane, and there's this plane spanned by this vector V2 and V3. We want to know those three planes. How far apart are they? What's the projective quadrants between them? That's what we're calling a spread. So in order to find that out, we would probably need to know what the perpendicular directions are. Given one of these planes, what's the vector that's perpendicular to one of these planes? And in our last few videos, we talked about sort of technology for finding such a polar triangle. So each one of these planes has a perpendicular direction. Since there are three planes, there are going to be three perpendicular directions, giving us another three lines through the origin. So we start with three lines through the origin, then we get another three lines to the origin, determined by the perpendicular directions of the planes generated by the original triangle. And how do we get at that polar triangle? Well, one way is through some linear algebra. So if we set up the matrix A, which is the matrix which has rows, the vectors that we're starting with, V1, V2, and V3, and we take the inverse of that matrix in the sense of linear algebra. There's the inverse. And we consider that to be the transpose of a matrix B. So this B will then be the transpose of that. There's the transpose where we replace rows with columns. Then the rows of this matrix B are then the direction vectors for these polar directions. So in this case, the W1 is the vector 1, 0, minus 2. That'll be 1 in this direction, 0 in the y direction, and minus 2 in that z direction. So the claim is that 1, 0, minus 2 is perpendicular to both V2 and V3. If you take the dot product between this thing and V2, you get 0. If you take the dot product between this and V3, you also get 0. Similarly, this one is the common perpendicular to V1 and V3. And this one here is the common perpendicular to V1 and V2. So to get the spreads of the original triangle, we're going to take these three vectors and calculate the quadrances of them. And that will be the spreads of the original triangle. So here's the picture that we have. There's our original vectors, V1, V2, V3. And now we have these new vectors, W1, W2, and W3. And then we can calculate the spreads S1, S2, and S3 of the original triangle by calculating essentially the quadrances between the W's. So S1 is the quadrants between W2 and W3. And we get the usual formula. Pretty simple because these vectors are very simple. We get 1. And S2 turns out to be 4/5, and S3 is 1. So in this case, this is a very simple triangle that we started with. We see some pleasant symmetry, that the spreads that we're getting are exactly the same as the quadrances that we got for the original triangle. The elliptic triangle A1, A2, A3 that we started with, and its polar triangle B1, B2, B3, which are the lines determined by these W directions, these are congruent. They have the same quadrances. Okay, so the picture that emerges. Here is our elliptic triangle represented by these 3 points on the sphere. So with this little spherical triangle that we see here, its quadrances are 1 here, and 4/5 here. And the spreads are 1, 1, and 4/5. Spread of 1 is the same as perpendicularity. So there's the table of quadrances and spreads for that elliptic triangle. And now we can check the various formulas for trigonometry. We can check Pythagoras' theorem. In fact, there will be 2 occurrences of Pythagoras' theorem because there's really 2 right triangles here. Okay. So, for example, since S1 is 1, there's S1 there, that spread at the vertex A1. The claim is that this quadrant's Q1 equals Q2 plus Q3 minus the product of Q2 and Q3. And because this is also a right angle here, or a perpendicularity, or a spread of 1, S3 is 1, therefore the Pythagoras' theorem applied to that situation would be that this quadrant's Q3 equals this quadrant's plus this quadrant's minus the product here. And then there's also the dual Pythagoras' theorem because we also have quadrances which are equal to 1. If we have a quadrant of 1 in a triangle, we also get a kind of Pythagoras' theorem, but involving the 3 spreads rather than the 3 quadrances. So since Q1 is equal to 1, since that Q1 is equal to 1, the relationship between the spreads are that this spread S1 is S2 plus S3 minus the product S2 times S3. And because Q3 equals 1, because this thing is 1, we must have that this spread S3 equals S1 plus S2 minus the product S1 times S2. And again, you have Thales' theorem that S2 is equal to Q2 over Q1, and S2 is also equal to Q2 over Q3, because there's 2 spreads which are equal to 1. And there's a dual Thales' theorem, because we have 2 quadrants is equal to 1. We can also say that Q2 is equal to S2 over S1, and it's also equal to S2 over S3. These are all relatively trivial to verify because the numbers are sort of pleasant. Now let's have a look at the spread law and the cross law. So here's a sort of a quick representation of our triangle. Here are the three quadrants and the three spreads again. And of course it's sort of obvious that the ratio of S1 over Q1 equals S2 over Q2 equals S3 over Q3. Each one of those quotients is equal to 1 immediately. And what about the cross law? Well, the cross law is useful here in that we could actually calculate the spreads from the trigonometry if we only knew the three quadrances. That's the role of the cross law, the dual cross law. If we know three quadrances or three spreads, we can generally get pretty good information about the other set. So here, for example, is the cross law involving S1. S1 Q2 Q3 minus Q1 minus Q2 minus Q3 plus 2 all squared is 4, 1 minus Q1, 1 minus Q2, 1 minus Q3. All right, so suppose that we know the three quadrances, but we don't know any of the spreads. Then this one we don't know, but Q2 times Q3 would be a 4/5. And we have to subtract this one, subtract this one, subtract this one, add 2. We just get minus 4/5 all squared. And because at least one of the quadrances is 1, we're going to get 0 on that right-hand side. That will tell us immediately that S1 has to be 1. So that spread has to be 1 as a consequence of the cross law if we only started with the quadrances. If we look at the corresponding cross law with the S2 term here, so S2 times Q1, Q3, and then proceeding similarly, then the Q1 times Q3 would be 1 times 1, the coefficient of 1. And here then we would get minus 4/5 again, squared equals 0. That would tell us that S2 is equal to 4/5. That spread would have to be 4/5. And similarly, S3 is equal to 1 the same way there. So this is showing the power of the cross law to actually calculate spreads from quadrances. All right, so this has been a very simple example. We're going to have a look at more complicated examples, but just to get us back into the framework of a little bit of rational trigonometry in 3 dimensions, this has been a good example to start with. Now I want to have a look at what the same triangle would look like in a classical point of view. What would classical spherical trigonometry have to say about the same spherical triangle? The classical view of a spherical triangle concentrates on the three angles, which we might call capital A1, capital A2, capital A3, and the three lengths of the sides, which say are correspondingly D1, D2, and D3. Okay, so in this same situation, if we use exactly the same points as before, then A1 and A3, those are right angles, so the angles themselves in the traditional sense are pi over 2. And the lengths of the sides, say D1 and D3, are also going to be pi by 2. I remind you that the way we measure lengths in the spherical trigonometry classically is as angles subtended from the center of the sphere. So if you're at the center of the sphere looking at this portion of this circle, you measure that angle, which happens to be 90 degrees, or pi by 2, and so you assign pi by 2 to be the length of that arc. That's the traditional viewpoint of spherical trigonometry. And what is pi by 2? Well, it's this number that starts 1.5707963267948966192 and carries on indefinitely to infinity. It's much less well known than 3.14159, etc., but arguably pretty well just as important, really. But let's just make sure we understand, right? This is an infinite process. An infinite amount of work would be actually required to generate the entire string here. So when we write pi by 2 like this, it's questionable to what extent we're really saying something completely precise, or whether we're just invoking a little symbolic notation to represent a process that we actually can't compute. Now what about D2? How do we calculate that classically? So we have two vectors, this vector v1 and vector v3. The classical formula for this D2 is the angle formed by those two vectors. And undergraduates learn the formula for the angle between two vectors. What you do is you take the two vectors, you take the dot product, then you divide by the length of the first vector times the length of the second vector, and all of that is the cosine of the angle. Right? So this d2, which is an angle, has the property that cosine of d2 is this quantity here. Now in order to calculate these lengths, there are square roots involved. So the dot product is simple enough, but there will be a square root of 5. So there's also an infinite process involved in actually calculating that square root of 5. But now the challenging part comes because you have to invert this to actually extract the angle d2. Undergraduates all learn how to press the appropriate buttons on their calculators. They know that there's a cos inverse or an arc cosine button. But what is that button actually doing? Well, it's invoking the first part of an infinite series. Okay. And the infinite series starts like this. So this pi over 2 minus x minus 1/6 x cubed minus 3 over 40 x to the 5th minus 5 over 112 x to the 7 minus 35 over 1152 x to the 9th minus 63 over 2816 x to the 11th, and so on. And there's a reasonably predictable pattern. If you stare at these numbers, you probably will be able to figure out what the pattern is. But there's also this pi by 2, which has this same infinite aspect built in. So the calculator takes 1 over root 5. Actually, it doesn't take 1 over root 5 because it doesn't have 1 over root 5. It has a decimal approximation to that. And then plugs it into here, suitably truncated, makes a calculation, which is again suitably truncated, and spits out something to the undergraduate making this calculation. The undergraduate says, aha, the angle d2 is, and then they get an answer. Typically, the calculator maybe only gives 8 decimal places or such, but anyway, the answer would be 1.10714871794090503, and so on. That is the angle formed here in this spherical triangle by these two vectors, and so that's the length, spherical length between these 2 points. So you can see that there's approximations going on here all over the place. We're truncating, we're dispensing with infinite things, we're introducing inaccuracies left, right, and center. Okay? And it's just deemed as part of the natural story here that this is the way classical spherical trigonometry operates. It's necessarily approximate. Whenever you do something, there are all these approximate values, and that's just the way it is. But you can see that the way we're looking at things, it's not that way at all. Okay, this alternate new point of view that we're proposing dispenses with all these irrationalities, all these transcendental quantities, all these infinite processes that we can't actually complete, and replacing them with algebraic calculations involving high school algebra, pen and paper. You make the calculation, at the end of a few minutes, you have an answer, and the answer is completely there. Everyone can see it, everybody can agree. It's like a difference between night and day to this classical theory. It is orders of magnitude superior to the classical theory. So let's have a look at this triangle and the more advanced laws in the context of this example. Classical triangle now with side lengths pi over 2, and d, and angles pi over 2, and d. D is this number 1.107 and so on that we've approximately calculated. So there's a Pythagoras' theorem. Because this is a right angle, there's a relationship between these 3 sides. And that relationship is that cosine of this side is the product of cosine of this times cosine of that. There's another Pythagoras' theorem which is dual to that. The sine law in this case is also seemingly trivial, that the sine of pi over 2 divided by the sine of that angle, which is pi over 2, is the same as the sine of this length over the sine of that angle, is the same as the sine of this length over the sine of that angle. Seemingly trivially true. And their cosine law, well, there are 2 of them. So this one here, for example, can be interpreted as a law that allows us to calculate an angle if we know the 3 side lengths. So the cosine of this length is the cosine of this times the cosine of that, plus the sine of this length times the sine of that length times the cosine of that angle. And so the other one is cosine of this angle is minus cosine of that angle times cosine of that angle plus sine of that angle times sine of that angle times cosine of that length. So because the cosine of pi by 2 is equal to 0 and sine of pi by 2 is equal to 1, these laws are pretty obviously sort of trivial from the outside. But in fact, when you think about it a little bit more deeply, you realize they're far from being trivial. I want to talk a little bit about that. So suppose we are a computer and we want to verify, say, this cosine law here. So what appears to us as a symbolical calculation, this cosine pi by 2 is equal to 0, is for the computer not at all so clear. It depends on how things are being represented. So if the computer has pi by 2 as a decimal, okay, then the cosine of pi by 2 calculation is something that it has to actually calculate. Okay, it will get something which is approximately 0. But still there's a significant calculation involved in making that approximate 0. Okay, so in fact, if you actually did this to many, many decimal places and actually worked things out very carefully, you could easily find that, you know, at the 100th decimal place, there's a difference between the left-hand side and the right-hand side. It's much more subtle than it appears. Of course, what we generally do at the undergraduate level is we restrict ourselves to these relatively simple angles like pi over 2, pi over 3, and pi over 4, and so on, for which we can just invoke values of, well, we know what cosine of pi by 2 is and we know what cosine of pi by 3 is. We don't actually have to calculate them. So classical trigonometry is built on this underlying assumption that we're going to try to avoid calculating things explicitly in a theoretical sense. We're only going to calculate when we move to approximations. So there's this division in the subject between the theoretical world, in which one is not really allowed to calculate, and the actual approximate reality in which the applications live. Okay? So from our point of view, this is unfortunate, and what we'd like to do is we'd like to have a theory where the theoretical business really incorporates the applications directly and completely. In other words, that we can actually make the calculations and verify that they're completely correct. There's a big difference between the rational calculations that we started this video with and these classical calculations. So once we move to more significant examples, the power of the rational point of view becomes overwhelmingly obvious. That's what we'll head towards next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.